To understand the history of dinosaurs, you must first forget the clock. Human civilization, the entirety of it, from the first crude clay tablets of Sumer to the glowing screens in your pocket, spans roughly 10,000 years. To a geologist, 10 millennia is not even a heartbeat. It is a single grain of sand on an endless beach. Dinosaurs, by contrast, ruled this planet for 165 million years. The human mind struggles to comprehend a span of time that vast. To make it tangible, imagine that the entire 4.5 billion-year history of Earth has been compressed into a single calendar year. If the planet formed on January 1st, the first simple bacteria do not appear until early March. The first multicellular life arrives in November. The dinosaurs do not step onto the stage until December 24th, at around 6 o'clock in the evening. They reign supreme through the holidays. They do not meet their ultimate demise until December 30th at 8 in the morning. Homo sapiens? We arrive on December 31st at 23 minutes to midnight. We are the final spark before the year ends. We have been here for mere minutes. The dinosaurs owned the day for weeks. Their story is not merely a fairy tale of giant monsters. It is a rigorous, staggering documentary of planetary mechanics. It is the story of how climate dictates biology, how continental drift creates and destroys empires, and how a single randomized impact from space can wipe the slate clean. It is a story of evolution's blind, relentless march, from unassuming dog-sized scavengers in a shattered world to the largest animals ever to walk on solid ground. We begin this journey not with a roar, but with silence. We begin in the ashes. Imagine standing on the surface of the Earth 252 million years ago. The air around you is heavy, toxic, and obscenely hot. It does not smell of earth or vegetation. It stings your lungs with the acrid bite of sulfur, carbon dioxide, and methane. The sky above is not the serene blue you are accustomed to. Instead, it is a sickly, bruised, yellowish gray, choked with a permanent, global smog of volcanic ash. You are standing at the absolute nadir of life's history on Earth. This is the Permian-Triassic extinction event, colloquially known as the Great Dying. Something terrible had happened to the planet's mantle. In what is now Siberia, a plume of superheated rock from the core had punched through the Earth's crust. It did not create a single volcano. It cracked the Earth open over an area the size of modern Europe. This was the Siberian Traps, a relentless, hemorrhaging wound in the planet's skin that erupted for hundreds of thousands of years. It spewed out enough lava to bury the continental United States under a mile of solid rock. But the lava was not the killer. The killer was the gas. Trillions of tons of greenhouse gases were injected into the atmosphere. The global temperature spiked. The oceans, which had been stable for millions of years, grew incredibly hot and highly acidic. As the water warmed, it lost its ability to hold dissolved oxygen. The once teeming seas of the Permian, filled with trilobites, ancient corals, and strange, armored fish, suffocated. The water turned into a stagnant, anoxic, black slime. Hydrogen sulfide gas bubbled up from the dead oceans, poisoning the air and shredding the ozone layer, allowing lethal ultraviolet radiation to scour the land. On land, the supercontinent of Pangaea, a massive, unbroken, C-shaped block of Earth, was turned into a wasteland. The great coal forests of the Carboniferous, the swamps that birthed the first amphibians and early reptiles, dried up and caught fire. Global wildfires raged, turning the sky red at night. 95% of all life on Earth died. 95 out of every 100 species were erased from the fossil record forever. If you took every 20 living things you see today and killed 19 of them, leaving only one alive, you would have a fraction of an idea of what the Great Dying accomplished. The world was a mausoleum. It seemed impossible that anything could survive, let alone thrive. But nature does not understand the concept of impossible. Nature only understands adapt or perish. Time passed. In human terms, an agonizingly long time, millions of years. But to the Earth, it was merely a cooling period. The Siberian volcanoes finally choked on their own magma and fell silent. The carbon dioxide in the atmosphere slowly began to be locked away by weathering rocks and the stubborn resilience of surviving plant life. Rains returned. At first they were acidic, burning the dead soil, but gradually they cleansed the land. This was the dawn of the Triassic period. Pangaea was still intact, but it was a harsh, unforgiving place. Because it was one giant landmass, the interior was thousands of miles from the ocean. There was no rain there. The heart of Pangaea was a brutal, scorching desert, baking under a sun unfiltered by ozone. Life could only cling to the coasts, to the fringes of the supercontinent where moist sea breezes brought rain and allowed stunted forests of primitive conifers, tree ferns, and horsetails to grow. The animals that emerged from the ashes of the Permian found an empty world. The ancient giants were gone. The ecological niches were vacant. It was an evolutionary free-for-all, a desperate land grab where only the most opportunistic survived. The rulers of this broken world were a group of animals known as the therapsids, the stem mammals. Creatures like Lystrosaurus, a pig-sized, barrel-chested animal with a turtle-like beak and two tusks, dominated the landscape. They were tough, they bred rapidly, and they seemingly owned the Triassic. Alongside them were the archosaurs, the ruling reptiles. This group would eventually give rise to crocodiles, pterosaurs, and dinosaurs. But in the early Triassic, they were small, skittish, and living on the margins. The true apex predators of this era were terrifying creatures like Saurosuchus. It was not a dinosaur. It was a Rauisuchian, a type of archosaur that looked like a crocodile stretched out on stilts. It grew up to 30 feet long. Its back was covered in overlapping armor plates. It had a massive skull with teeth designed to crush bone. When Saurosuchus walked through the Triassic riverbeds, the ground shook. It was the undeniable king of the food chain. And hiding in the bushes, darting between the legs of these armored monsters, were the first dinosaurs. If you were transported back to the Ischigualasto Formation in what is now Argentina, a moon-like valley of red sandstone and badlands, you would struggle to spot a dinosaur. They were visually insignificant. They were not the monsters of Hollywood fame. They were the size of chickens, or perhaps a medium-sized dog. One of the earliest true dinosaurs we know of is Eoraptor lunensis, the dawn plunderer. It was barely 3 feet long. It walked on 2 legs, balancing its body with a long, thin tail. It had a small head, lightweight hollow bones, and a mouth full of curved, sharp teeth mixed with flatter leaf-shaped teeth. It was an omnivore, eating whatever it could find: insects, small lizards, bits of carrion, and tough ferns. Another was Eodromeus, the dawn runner. Slightly longer and leaner than Eoraptor, it was a dedicated predator, but it weighed no more than a large house cat. Why did these tiny, fragile creatures survive, while the massive armored reptiles around them eventually perished? The answer lies not in size, but in engineering. The dinosaurs possessed a suite of anatomical innovations that, while invisible to the casual observer, were the keys to planetary domination. First, consider how a lizard runs. Its legs sprout out sideways from its body. When it moves, its torso sags to the ground, bending from side to side. It is essentially doing push-ups with every step. This is exhausting and highly inefficient. The early dinosaurs did something revolutionary. They stood up. Their femurs were drawn directly underneath their bodies, perpendicular to the ground. Their knee joints were angled backward, and their ankle joints were modified into a hinge. They were fully erect. This simple change in posture had profound consequences. It meant their lungs were no longer being compressed by a sagging torso with every step. They could breathe continuously while running. They had vastly increased stamina. While a Rauisuchian could burst forward in a terrifying ambush, it quickly tired. A dinosaur could jog for miles. Furthermore, dinosaurs evolved a highly efficient bird-like respiratory system, possibly involving air sacs that pumped fresh oxygen through stiff lungs in a one-way loop. In the low-oxygen, stuffy atmosphere of the recovering Triassic, this made them hyper-efficient at extracting every possible molecule of oxygen from the air. Finally, there was the hip structure. The very word dinosaur translates to terrible lizard, a name coined by Sir Richard Owen in 1842. But they were not lizards. Owen noticed a distinct arrangement in their pelvic bones, a structure that held the legs firmly beneath the body. Later paleontologists would split dinosaurs into two great branches based on their hip design: the Saurischia, lizard-hipped, which included the meat-eaters and the giant longnecks, and the Ornithischia, bird-hipped, which included the horned and armored plant-eaters. Ironically, modern birds evolved from the lizard-hipped dinosaurs, not the bird-hipped ones, a quirk of evolution that delights and confuses scientists to this day. In the early Triassic, these anatomical marvels were merely survival traits. They allowed Eoraptor to escape from Saurosuchus. They allowed early dinosaurs to exploit niches that required speed and agility. They were the underdogs, biding their time in the shadows, waiting for the world to change. And the world was about to change. Violently. The Triassic continued. The giant Rauisuchians grew larger. The Dicynodonts spread across the globe. It seemed the dinosaurs would remain minor characters in the grand narrative of life. But the Earth is a restless planet. Tectonic plates shift, magma pools, and climates fluctuate with devastating suddenness. Around 232 million years ago, at the boundary between the early and late Triassic, an interval known as the Carnian stage, the planet suffered another massive climate shock. Once again, massive volcanic eruptions occurred, this time likely in the Rangelia province of western North America, where huge basalt plateaus formed on the ocean floor and erupted onto islands. The effect was global. The climate, which had been dry and hot, suddenly flipped. Geologists call this the Carnian pluvial episode, the Carnian rain. For a period of roughly 1 to 2 million years, it rained relentlessly across Pangaea. The great inland deserts were flooded. Rivers swelled to unprecedented sizes, dumping vast amounts of sediment into the sea. This extreme, unending humidity was a death sentence for the dominant flora of the Triassic. The primitive seed ferns and conifers that had survived the Great Dying could not cope with the saturated soils. They rotted at the roots and died off in staggering numbers. When the plants die, the plant-eaters die. When the plant-eaters die, the apex predators starve. The heavy, armored Rauisuchians and the bulky Dicynodonts, adapted for the harsh, dry conditions, were systematically wiped out by the endless monsoon. The ecological tables of the Triassic were swept completely clean. But in the devastated, waterlogged soils, a new type of plant was waiting in the wings. A more advanced type of conifer, adapted to wetter conditions and capable of faster growth, exploded across the globe, replacing the dead forests. And who was best adapted to eat this new vegetation, navigate the flooded, muddy landscapes, and outcompete the starving survivors? The underdogs, the dinosaurs. The endless rains of the Carnian pluvial episode eventually subsided. The climate stabilized, but the world was fundamentally changed. The slow, lumbering dicynodonts were ghosts of the past, reduced to a few dying lineages. The terrifying Rauisuchians, the apex predators that had kept the early dinosaurs in constant fear, were severely depleted, their heavy bodies and slow reproductive rates unable to cope with the rapid environmental shifts. Nature abhors a vacuum. With the terrestrial ecosystems shattered and the old guard weakened, the evolutionary gates were blown off their hinges. The dinosaurs, those small, bipedal, highly efficient, fast-breeding creatures, experienced what paleontologists call an adaptive radiation. They exploded in diversity, splitting into wildly different body plans to fill the empty roles in the food web. If we walk through the Ischigualasto Valley of Argentina during this time, the landscape looks different. The ferns and primitive conifers are thick, watered by sprawling rivers. And now, the dinosaurs are no longer hiding in the underbrush. They own the daylight. We see the first truly terrifying dinosaurian predators. Herrerasaurus strides into the clearing. It is a massive leap forward from the little Eodromeus. Reaching up to 20 feet in length and weighing nearly half a ton, Herrerasaurus is a sleek, bipedal killing machine. It walks on powerful bird-like legs balanced by a heavy, stiffened tail. Its skull is long and low, filled with serrated, steak-knife teeth that curve backward to prevent prey from escaping. It has a specialized joint in its lower jaw that allows it to flex backward slightly, accommodating larger chunks of meat. It is the prototype for the great theropod killers that will define the Mesozoic. Yet, Herrerasaurus is a primitive killer. It still has 5 fingers on its hands. Though the 4th and 5th are tiny, it is a transitional form, a bridge between the small, dog-like hunters of the early Triassic and the colossal hypercarnivores of the Jurassic. But for now, in the late Triassic, it is the undisputed king of the South American floodplains. Meanwhile, in the exact same ecosystems, another evolutionary experiment is taking place. Some of the early meat-eaters or omnivores decided to stop eating meat altogether. Plants are abundant, and there is less competition at the bottom of the food chain. But plants are difficult to digest. They are made of tough cellulose. To survive on plants, an animal needs a massive gut to ferment and break down the vegetation, and it needs to eat a lot of it. This led to the birth of the sauropodomorphs, the lineage that would eventually produce the largest land animals in Earth's history. In the late Triassic, we see their early vanguard, animals like Saturnalia and Eoraptor's larger cousin, Pantidraco. They are still bipedal, still looking somewhat like predators, but their necks are beginning to stretch. Their teeth are no longer sharp and curved. They are leaf-shaped, designed for stripping foliage. Their bodies are getting heavier, their bellies expanding to house massive digestive tracts. Move forward a few million years, crossing the nascent supercontinent to what will become Europe and North America, and the sauropodomorph experiment has reached a new extreme. Enter Plateosaurus. If you saw a Plateosaurus, you would immediately recognize it as something entirely new. It is huge, growing up to 33 feet long and weighing close to 2 tons. But it is an animal caught in an evolutionary halfway house. It still walks primarily on its 2 back legs, which are massive and pillar-like, ending in broad, fleshy feet that distribute its enormous weight. But its neck is absurdly long, making up nearly 1/3 of its total body length, balanced by an equally long, whip-like tail. Plateosaurus was not a grazer. It was a browser. It used its long neck to reach into the mid-canopy of coniferous trees, stripping branches clean of needles with its spatulate teeth and swallowing them whole without chewing. Its massive gut, housed in its barrel-shaped body, did all the work. We know a staggering amount about Plateosaurus because of a remarkable fossil site in Germany, the Trossingen Quarry. Here, paleontologists have found the bones of over 100 individual Plateosaurus specimens, jumbled together. For decades, scientists thought these were herds that died together in a catastrophic flood. But modern forensic taphonomy, the study of how things fossilize, tells a different, darker story. These bones show no signs of being washed together by water. They are found in mudstone, representing stagnant, drying ponds. During severe droughts, Plateosaurus likely gathered around the last remaining water holes. As the ponds dried up, the weakest individuals collapsed and died of thirst and starvation, their bodies piling up in the mud over decades. It is a stark reminder that, despite their growing size, the dinosaurs were still at the mercy of a brutal, unforgiving climate. Yet, even in death, Plateosaurus proves its success. It was the most common large animal of its time. It had solved the puzzle of bulk feeding. The era of the giants was officially beginning. The slow, heavy armored reptiles of the Permian and early Triassic were obsolete. Speed, stamina, and rapid growth were the new metrics of evolutionary success, and the dinosaurs had perfected them. The Triassic period was drawing to a close. The world was restless again, but this time the shifting was not just atmospheric, it was tectonic. For tens of millions of years, the supercontinent of Pangaea had acted like a giant pressure cooker. Heat built up beneath its massive, unbroken continental crust, unable to escape into the oceans as it does on modern Earth. Finally, the pressure exceeded the strength of the rock. Pangaea began to rip apart. A massive fault line cracked open between what is now North America and Africa. This tectonic wound did not heal, it widened, and as the crust thinned and stretched, the mantle beneath it melted, rising to the surface in an apocalyptic display of volcanic fury. This geological nightmare is known as the Central Atlantic Magmatic Province, CAMP. Over a period of perhaps just a few 100,000 years, an area of land larger than modern Europe was flooded with lava. Volcanoes erupted continuously, spewing billions of tons of sulfur dioxide, carbon dioxide, and chlorine into the atmosphere. The oceans acidified once again. The global temperature spiked, and the climate swung wildly from hyper-warm to freezing cold in a geological blink of an eye. This was the end Triassic extinction. It was the fourth of Earth's Big Five mass extinctions. Once again, the land was purged. The last of the giant amphibians were wiped out. The remaining Rauisuchians, those crocodile-like apex predators that had terrorized the early dinosaurs, were completely annihilated. Most of the early mammal-like reptiles were pushed to the absolute margins of existence, forced to become tiny, nocturnal insect eaters to survive. And the dinosaurs? They suffered. Fossil records show a distinct drop in dinosaur diversity at the exact boundary of the extinction event. They were not immune to the apocalypse, but they possessed a combination of traits that allowed them to weather the storm far better than their competitors. Their high metabolisms allowed them to remain active when the climate cooled. Their efficient respiratory systems handled the fluctuating atmospheric gases, and, crucially, their rapid growth rates and high reproductive output meant that if a population was decimated by a drought or a freeze, it could bounce back within a few generations. The slow-breeding archosaurs simply could not recover fast enough. When the volcanoes of Camp finally fell silent and the ash began to clear, the world looked profoundly different. Pangaea was gone, replaced by two smaller supercontinents, Laurasia in the north and Gondwana in the south, separated by a young, narrow, and shallow ocean called the Tethys Sea. The stage was cleared. The old monsters were dead, and the dinosaurs, battered but resilient, stepped out of the ashes to claim their rightful inheritance. The Jurassic period had begun. The name Jurassic comes from the Jura Mountains in Switzerland, where limestone rocks of this age were first studied. But the Jurassic world was vastly different from the alpine landscapes of modern Europe. The climate was uniformly warm. There were no ice caps at the poles. Sea levels were extraordinarily high because the hot temperatures had caused the oceans to expand, and the newly formed shallow ocean basins were overflowing. Laurasia and Gondwana were heavily fragmented, creating vast archipelagos, shallow inland seas, and endless stretches of humid tropical coastlines. It was a perfect world for plants. Coniferous forests exploded in diversity, creating towering jungles of araucarias, the ancestors of modern monkey puzzle trees, podocarps, and massive ginkgos. Cycads, short palm-like plants with thick trunks and crowns of tough, leathery fronds, carpeted the forest floors. And into this lush, endless greenhouse walked the true giants. The sauropodomorphs, which had been experimenting with larger sizes and longer necks throughout the late Triassic, finally committed fully to a new lifestyle. They dropped down onto all fours. Their back legs remained massive, but their front legs grew to match them. Their necks elongated to absurd, physics-defying proportions. Their tails became thick, muscular whips to counterbalance their massive necks. Their bodies expanded into gigantic fermentation vats. Some of the earliest true sauropods, like Vulcanodon from southern Africa, were relatively modest, maybe 30 feet long, but the evolutionary trajectory was set. The logic of the sauropod was relentless. If you can reach higher into the trees than any other herbivore, you have a monopoly on food. If you are too big for any predator to kill, you are safe. Natural selection drove them upward and outward. Walking alongside these earliest giants were the true architects of the Jurassic terror, the theropods. The small, agile predators of the Triassic had evolved. Dilophosaurus appeared in the early Jurassic of North America. It was a spectacular animal, reaching 20 feet in length. It had a pair of thin, bony crests running along the top of its skull, likely used for display or species recognition. It was slender, built for speed, and its jaws were lined with long, thin, recurved teeth designed for slashing flesh rather than crushing bone. It was not a titan yet, but it was a stark warning of what the meat-eating dinosaurs would eventually become. And then there were the ornithischians, the bird-hipped dinosaurs. Throughout the Triassic, they had been incredibly rare, but in the Jurassic, they began their own evolutionary radiation. Lesothosaurus, a tiny bipedal plant eater from southern Africa, scurried through the underbrush. It looked somewhat like a rabbit, with large eyes and a beak for snipping leaves. It was the primitive template for an entire lineage that would eventually produce the horned ceratopsians and the duck-billed dinosaurs. The Jurassic dawn was a time of unfathomable opportunity. The ecological niches were wide open. The air was warm, the ground was wet, and the vegetation was inexhaustible. The dinosaurs had survived two of the worst mass extinctions in planetary history. They were not going to squander their third chance. They were about to grow to sizes that the Earth had never before seen and will never see again. Chapter 9. The Physics of the Impossible. 155 million years ago. To truly understand the Middle and Late Jurassic, you must completely abandon your sense of scale. We have entered the era of the sauropods, and they committed to a lifestyle that defies the laws of physics as we understand them for terrestrial animals. How does an animal get to be the size of a building? Today, the largest land animal is the African elephant, weighing in at around 6 or 7 tons. That is the absolute biological limit for a modern mammal. If an elephant were to double in size, its bones would shatter under its own weight, and its heart would be incapable of pumping blood up its long neck. But in the late Jurassic, the rules were different. The atmosphere was richer in oxygen and carbon dioxide, supporting an incredibly lush, high-calorie environment. But more importantly, the sauropods evolved a biological engineering marvel. They hollowed themselves out. If you were to look at the skeleton of a Brachiosaurus, one of the most iconic giants of the Jurassic, you would notice something startling. Its bones are riddled with holes. They are not solid blocks of calcium. They are riddled with pneumatic cavities, hollow spaces connected to a system of air sacs that ran throughout the animal's body, much like the respiratory system in modern birds. This avian-style respiratory system did two things. First, it allowed the animal to extract oxygen far more efficiently than a mammal could. Second, it dramatically reduced the weight of the skeleton. A Brachiosaurus could reach lengths of 80 feet and weigh upwards of 50 tons, yet its bones were remarkably light for their size. It was a biological dirigible, a massive frame supported by a skeleton made of structural scaffolding rather than solid rock. Then there was the neck. Brachiosaurus was a high browser. Unlike its later relatives, its front legs were significantly longer than its back legs, giving it a giraffe-like posture. Its neck rose vertically into the air, topped by a relatively small skull. The engineering challenge here is astronomical. To get blood from the heart of an 80-foot animal up a 30-foot vertical neck to its brain requires a blood pressure that would blow out the blood vessels of any human. Paleontologists believe the sauropod heart was a massive, 4-chambered engine, weighing perhaps hundreds of pounds, beating with enough force to propel a column of blood straight up against gravity. To prevent the blood from pooling in their lower legs when they stood still, their veins likely had a series of one-way valves, exactly like the veins in a giraffe's neck. Brachiosaurus was a slow-moving, placid giant. It did not chew its food. Its teeth were blunt, spoon-shaped pegs, perfect for raking in massive quantities of tough conifer needles and cycad fronds. It would strip a branch bare, swallow the foliage whole, and drop it into a fermentation vat of a stomach that likely housed gut microbes capable of breaking down toxic plants and tough cellulose. To maintain a 50-ton body, a Brachiosaurus had to consume hundreds of pounds of vegetation every single day. It was a walking, breathing, industrial processing plant. While Brachiosaurus reached for the heavens, other sauropods took a different evolutionary path. If Brachiosaurus was a giraffe, Diplodocus and its close relative Apatosaurus were suspension bridges. Found primarily in the Morrison Formation of North America, a vast fossil bed stretching from New Mexico to Montana, these diplodocid sauropods were incredibly long. Diplodocus could reach 110 feet in length, but most of that was neck and tail. Their bodies were relatively slender, and their necks extended horizontally, parallel to the ground. They were not high browsers. They were mid to low browsers, sweeping their necks back and forth over a massive arc, like the arm of a construction crane, stripping ferns and low-lying conifers. The tail of Diplodocus is one of the most extraordinary structures in the history of vertebrate evolution. It is incredibly long, thin, and tapering. For a long time, scientists believed the tail simply dragged on the ground behind the animal. But modern biomechanical studies have proven otherwise. The tailbones beneath the skin were held off the ground by strong ligaments. It was held stiffly out behind the animal as a counterbalance to its immense neck. But the most extreme hypothesis regarding the Diplodocus tail emerged in the late 20th century. Paleontologists realized that the very end of the tail, the last 30 or 40 vertebrae, were reduced to simple rods of bone, resembling the handle of a bullwhip. Computer models suggested that if a Diplodocus flicked its tail from side to side, the motion would travel down the length of the tail, amplifying in speed as it went, until the very tip broke the sound barrier, creating a sonic boom. While the idea of a supersonic dinosaur is thrilling and highly debated, most scientists now think a supersonic crack would shatter the fragile tip bones. There is no doubt the tail was used as a formidable weapon. A full lateral swing of a 40-foot tail would strike a predator with the force of a falling tree. Apatosaurus, once famously confused with Brontosaurus due to a century-old paleontological mix-up involving mismatched skulls, was even more heavily built than Diplodocus. It had a massive, bulky neck and a thick, whip-like tail. It was a tank, protected not by armor, but by sheer, overwhelming mass. These animals lived in herds. We know this because of sites like the Carnegie Quarry in Dinosaur National Monument, Utah. Here, an ancient riverbed acted as a giant trap. During droughts, sauropods would gather around the shrinking river. When they died of starvation or dehydration, their massive bodies were washed downstream and jammed into a sandbar, creating a massive bone bed containing the remains of dozens of individuals, from juveniles to elders. It is a stark, beautiful testament to their gregarious nature. To walk through the Morrison Formation during the late Jurassic is to walk through an ecosystem that has no modern equivalent. It has been termed the Jurassic Serengeti, but this understates the reality. The climate was seasonal. It was not a uniform tropical paradise. It was a vast, flat floodplain crossed by meandering, braided rivers. During the wet season, the land would flood, creating lush, green savannas of ferns and horsetails. During the dry season, the land would parch, turning to dust, forcing massive migrations of herbivores toward the permanent water sources. The flora was alien. Grass did not exist. Grasses are a relatively recent evolutionary invention, arriving only after the dinosaurs died out. The ground was covered in a dense, knee-to-waist high mat of primitive ferns, club mosses, and equisetums, horsetails. Towering above them were the conifers, massive araucarias, towering redwood ancestors, sequoias, and ginkgo trees. Interspersed among them were cycads, short, stout-trunked plants with crowns of tough, leathery leaves that looked somewhat like palms, though they are completely unrelated. It was a landscape painted in greens and browns, lacking the bright flowers of the modern world. Flowering plants, angiosperms, had not yet evolved. There were no apples, no roses, no grassy meadows. The color palette of the Jurassic was somber, dominated by the dark green of conifers and the dusty brown of dry earth. In this environment, the giant sauropods were the ecosystem engineers, by knocking down trees with their sheer bulk to reach the upper canopy leaves, and by stripping vast acres of vegetation bare, they created clearings. Their massive droppings, rich in undigested plant matter, fertilized the soil and supported vast colonies of insects and small scavengers. They shaped the world around them, just as elephants do in Africa today, but on a monumental scale. And where there are massive herds of prey, there are predators. The apex predator of the Morrison Formation was not a Tyrannosaurus. T-Rex would not evolve for another 85 million years. In the Jurassic, the role of the top carnivore belonged to Allosaurus. Allosaurus fragilis, the fragile lizard, a rather ironic name for an animal that routinely hunted animals 10 times its size. An adult Allosaurus measured around 35 to 40 feet in length and weighed roughly 2 tons. It was built for speed and aggression. It had long, powerful hind legs, a deep tail for balance, and relatively long arms ending in 3 massive hooked claws. But its most terrifying feature was its skull. The skull of Allosaurus was a marvel of predatory engineering. Unlike the thick, blunt skull of a T-Rex, the Allosaurus skull was light, consisting of thin struts of bone, separated by large open spaces, fenestra. It was like a suspension bridge, incredibly strong but remarkably light. Its teeth were not thick railroad spike teeth. They were thin, serrated, and slightly curved backward, like the teeth of a Komodo dragon. They were not designed for crushing bone. They were designed for slicing flesh. Furthermore, Allosaurus possessed a bizarre evolutionary quirk. Above its eyes, it had a pair of bony ridges. In front of those ridges, in the roof of its mouth, it had a joint that allowed its upper jaw to flex upward. Combined with incredibly flexible neck muscles, Allosaurus could open its mouth incredibly wide, almost like a snake, and drive its upper teeth down into a target with a chopping, axe-like motion. How did a 2-ton predator take down a 50-ton sauropod? The answer is, it probably didn't, at least not a healthy adult. Allosaurus was an opportunist. Fossil evidence paints a picture of a creature that targeted the weak. We find Allosaurus bite marks on sauropod bones, but they are often on the lower legs or ankles, suggesting the predator would dart in, slash at the hamstring or ankle of a giant, and then step back to wait for the animal to bleed out or succumb to infection. We also know Allosaurus was not above eating its own kind. The famous Cleveland Lloyd Dinosaur Quarry in Utah contains the remains of over 40 Allosaurus individuals, but almost no other species. Paleontologists are puzzled by this, but the leading theories suggest that during severe droughts, Allosaurus individuals gathered around shrinking muddy water holes, and when the larger prey died off, they turned to cannibalism. Many of the Allosaurus bones at the quarry bear deep bite marks from other Allosaurus. There is even direct evidence of combat between Allosaurus and another iconic Jurassic herbivore. A famous Stegosaurus neck plate found in the Morrison Formation has a massive U-shaped bite mark perfectly matching the jaw of an Allosaurus. And conversely, an Allosaurus tail vertebra has been found with a massive, cone-shaped hole punched clean through it, the exact size and shape of a Stegosaurus tail spike. This brings us to Stegosaurus, perhaps the most anatomically bizarre animal to ever walk the earth. Stegosaurus was a heavy, slow-moving herbivore, weighing up to 5 tons. Its brain was absurdly small, roughly the size of a walnut or a dog's brain. For a long time, this led to the myth that Stegosaurus was incredibly stupid, a prehistoric punchline. In reality, a brain is an energy-expensive organ. Stegosaurus simply did not need a large brain to eat low-lying ferns and defend itself. It relied on instinct and heavily automated nervous system responses. Its back was lined with two alternating rows of massive, diamond-shaped bony plates. These plates were not armor. They were covered in a thin layer of skin and richly supplied with blood vessels. If you look at a cross-section of a Stegosaurus plate, it looks like a radiator. The primary function of these plates was almost certainly thermoregulation. By flushing blood into the plates, the animal could absorb heat from the morning sun to warm up its cold-blooded body. By turning the broad side of the plates away from the sun or facing into a breeze, it could cool down. Secondary to thermoregulation, they were likely used for display. The plates would change color as blood flushed into them, allowing Stegosaurus individuals to signal aggression, submission, or mating readiness to one another. But its true weapon was at the end of its tail. 4 massive, 3-foot-long bony spikes called thagomizers, a name coined in homage to a Far Side comic strip which has since been adopted into formal paleontology. These spikes were not just for show. As we saw with the injured Allosaurus, a swing of that spiked tail could drive a cone of bone straight through the flesh and muscle of an attacking predator. Stegosaurus was not defenseless prey. It was a living medieval mace. The Jurassic period was a masterpiece of evolutionary equilibrium. The giant sauropods cleared the forests. The medium-sized herbivores like Stegosaurus and Camptosaurus kept the undergrowth in check, and the Allosaurus population kept the herbivore populations healthy by culling the sick and the weak. It was a golden age, an age of giants. But the Earth's tectonic engine never stops turning. The continents continued to drift, the seas continued to rise and fall, and the climate was slowly, imperceptibly beginning to change. The Golden Age would not last forever. The stage was being set for the final, most dramatic act of the Mesozoic, the Cretaceous. Nothing lasts forever, not even a Golden Age. The Jurassic period drew to a close not with a catastrophic asteroid strike or a volcanic apocalypse, but with a slow, grinding, geological sigh. The supercontinents of Laurasia in the north and Gondwana in the south, which had already begun to pull apart, continued their tectonic drift. The Earth's crust stretched, buckled, and fractured. As the Cretaceous period began, the map of the world was being fundamentally redrawn. The North Atlantic Ocean began to open, slowly pushing North America away from Europe. South America and Africa started their long, millions of years divorce, widening the South Atlantic. In the Southern Hemisphere, India broke away from Antarctica and began a slow, lonely drift northward toward Asia, a journey that would eventually result in the Himalayas, though that was far in the future. This continental shattering had a profound biological consequence: isolation. In the Jurassic, a dinosaur could theoretically walk from what is now Colorado to what is now Tanzania without ever seeing the ocean. Land bridges connected the continents, but in the Cretaceous, rising sea levels flooded the low-lying continental interiors, creating vast, shallow inland seas. The most famous of these was the Western Interior Seaway, which split North America in half, running from the Arctic Ocean down to the Gulf of Mexico. Evolution hates a vacuum, but it loves a barrier. When populations of the same species are separated by oceans or impassable mountain ranges, they stop interbreeding. Mutations accumulate. Different environments favor different traits. This process, called vicariance, caused the dinosaurs to splinter into wildly different regional factions. The dinosaurs of Cretaceous South America evolved in total isolation from those of Cretaceous Asia. The dinosaurs of Europe reduced to a scattered archipelago of tropical islands by the rising Tethys Sea, evolved into dwarf species. The era of the globally uniform dinosaur was over. The era of regional specialization had begun. As the continents broke apart, the plant kingdom underwent a revolution that would permanently alter the trajectory of life on Earth. For over 100 million years, the landscape had been a monotony of green and brown. Conifers, cycads, ferns, and ginkgos dominated. They were resilient, but they had a flaw. Their reproductive strategies were slow and inefficient. They relied on wind to carry their pollen and spores, which required producing massive amounts of it in the hopes that a few grains would land on a receptive seed. Then, in the early Cretaceous, a new type of plant appeared. It did not rely on the whims of the wind. It produced a specialized structure, a flower, designed to attract insects. The insects, lured by nectar, would unknowingly carry pollen from flower to flower with pinpoint accuracy. These were the angiosperms, the flowering plants. The evolutionary partnership between insects and flowers was a nuclear detonation in the slow-paced world of Mesozoic botany. Flowering plants grew faster, reproduced more efficiently, and adapted to a wider variety of environments than conifers. Within a few million years, they began to spread across the globe, pushing into disturbed soils, riverbanks, and forest edges. This botanical revolution forced a crisis upon the herbivorous dinosaurs. The giant sauropods, with their blunt, peg-like teeth and massive fermentation guts, were perfectly adapted to eating tough, fibrous conifer branches. They were poorly equipped to deal with the new, fast-growing, often smaller, flowering plants. As the Cretaceous progressed, the sauropods began to vanish from many parts of the world. In North America and Europe, they were entirely replaced by a new breed of herbivore, the ornithopods. The quintessential ornithopod of the early Cretaceous was Iguanodon. First discovered in 1822 by Marianne and Gideon Mantell in England, Iguanodon was one of the very first dinosaurs ever described, alongside Megalosaurus and Hylaeosaurus, the trio that inspired Sir Richard Owen to coin the word Dinosauria. But the Iguanodon of the early Cretaceous was a far cry from the sluggish, lizard-like creature the Victorians initially imagined. Iguanodon was a masterpiece of evolutionary engineering. It grew up to 30 feet long and weighed around 3 to 4 tons. It was capable of walking on all fours, but its pelvis was structured in such a way that it could easily rear up onto its hind legs to run on 2 legs or to reach higher foliage. Its spine was reinforced by a network of ossified tendons, tough, bone-like cords that ran along its back, keeping its tail stiff and its body balanced without the need for heavy muscle. But its most remarkable feature was in its mouth and hands. Iguanodon had a highly specialized skull. Instead of a beak or peg teeth, it possessed a dental battery. Its jaw was packed with dozens of closely packed teeth that formed a grinding surface. As the top teeth wore down from chewing, new teeth continuously grew up from the jawbone to replace them, like a conveyor belt. Iguanodon could chew. It could grind up tough, fibrous plants, including the new flowering weeds and shrubs, into a digestible pulp. This was a massive energetic advantage over sauropods, who swallowed their food whole and let their guts do the work. Chewing extracts nutrients faster and more efficiently. At the end of its 5-fingered hands, Iguanodon possessed a bizarre weapon. Its thumb had evolved into a massive, conical, spike-like claw, often measuring several inches in length. For over a century, scientists were baffled by this spike. Gideon Mantell initially placed it on the animal's nose, thinking it was a horn. We now know it was a thumb spike. What was it used for? Defense against predators seems likely, but the spike was attached to a heavily muscled thumb that could move in a wide arc. Modern biomechanical studies suggest it could have been used in intra-species combat, males fighting for dominance or mating rights by slashing at each other's flanks or necks, or even for piercing through the tough skins of fallen fruits to get at the pulp inside. Iguanodon was wildly successful. We have found their fossils all over the world, from Europe to North America to Asia and North Africa. They traveled in massive herds, migrating across the shifting floodplains. In Europe, they evolved into dwarf forms on the isolated islands, shrinking to the size of a pony due to the limited resources of island life. They were the deer and bison of the Cretaceous world. While the ornithopods conquered the land, a terrifying new branch of the theropod family tree was conquering the rivers: the Spinosaurids. If Allosaurus was a wolf of the Jurassic, Spinosaurus was something entirely alien. Spinosaurus aegyptiacus lived in what is now the Sahara Desert, but 112 million years ago, that region was a vast, humid, river-filled swamp system, teeming with giant fish, crocodiles, and freshwater plesiosaurs. Spinosaurus was the largest terrestrial carnivore to ever live. It dwarfed Tyrannosaurus rex, reaching lengths of over 45 feet and weighing up to 8 or 9 tons. But it was not built like a typical theropod. Its back was crowned with a series of enormous, bony spines, some reaching over 5 feet tall. In life, these spines were covered in a thick layer of skin and fat, forming a massive sail. The function of this sail is debated. It could have been for thermoregulation, or perhaps a display structure to attract mates or intimidate rivals. More bizarre than the sail, however, was its anatomy. Spinosaurus had a skull that looked exactly like that of a modern crocodile. A long, narrow, studded with conical, interlocking teeth, designed not for slicing flesh, but for catching slippery, writhing fish. And then there were the bones. Paleontologists examining the dense bone structure of Spinosaurus realized something shocking. Its bones were solid, like the bones of a penguin or a manatee, not hollow like the bones of other theropods. This is an adaptation seen in animals that spend a lot of time in the water. Solid bones act as ballast, help the animal dive and stay submerged. Furthermore, its hind legs were incredibly short and stumpy for its massive size, while its feet were likely webbed. It could not run fast on land. It was an aquatic predator. Spinosaurus would wade into the rivers, using its crocodilian snout to sense the vibrations of fish in the murky water, snapping them up with terrifying precision. It was the only known dinosaur to have fully adapted to a semi-aquatic lifestyle, occupying the ecological niche of a giant grizzly bear crossed with a crocodile. It was an evolutionary dead end, a bizarre specialization. But it perfectly illustrates how the fragmented, diverse environments of the Cretaceous allowed dinosaurs to explore lifestyles that were previously unimaginable. Our understanding of dinosaurs was revolutionized in the 1990s, not by a giant skeleton in the American West, but by a series of spectacularly preserved slabs of limestone in northeastern China. This region, known as the Yixian Formation, part of the larger J-hole biota, was a landscape of shallow lakes and dense forests, dominated by early flowering plants and conifers, ringed by active volcanoes. Periodically, these volcanoes would erupt, belching out clouds of toxic gas and fine silica-rich ash. Birds, small mammals, pterosaurs, and small dinosaurs would die instantly from the poison gas or suffocate as the ash settled over the lakes. Their bodies would sink to the bottom, where a lack of oxygen prevented decay. The fine ash settled over them like a soft blanket, preserving them in astonishing, microscopic detail. These fossils are two-dimensional. They look like pressed flowers. But the detail they preserve is unparalleled in the fossil record. We do not just find bones. We find outlines of skin. We find the delicate, lattice-like structure of lungs. We find stomach contents. And most extraordinarily, we find feathers. The Yixian Formation proved, beyond a shadow of a doubt, that a vast array of theropod dinosaurs, not just the direct ancestors of birds, but distant cousins, were covered in feathers. Sinosauropteryx, a small two-legged predator about the size of a turkey, was covered in a dense coat of simple, hair-like proto-feathers called dino fuzz. And incredibly, chemical analysis of the fossilized melanosomes, the pigment-producing structures in feathers, revealed its coloration. Sinosauropteryx was covered in a reddish-brown coat with a banded, raccoon-like tail of alternating dark and light stripes. It looked less like a scaly reptile and more like a strange, long-tailed mammal. Then there was Microraptor, a tiny, crow-sized dromaeosaurid. It did not just have fuzzy insulation, it had true, complex, asymmetrical flight feathers on both its arms and its legs. It was a four-winged dinosaur. It could not fly like a modern bird, but it could glide from tree to tree in the dense Cretaceous forests, hunting insects and small lizards. These Chinese fossils shattered the image of the dinosaur forever. The giant, scaly monsters of our childhood imaginations were an illusion. The truth is that dinosaurs were vividly colored, highly active, often feathered animals. Tyrannosaurus rex, as a theropod, almost certainly had at least some feathers, at least when it was young, acting as insulation before it grew large enough for its sheer mass to retain heat. The Johol biota captured a snapshot of the Cretaceous in action. It showed us dinosaurs brooding over their eggs like birds. It showed us dinosaurs with iridescent, shiny black feathers, like modern crows. It showed us that the sky in the Cretaceous was not just ruled by pterosaurs, but by a bewildering variety of bird-like dinosaurs experimenting with flight. The world was becoming more colorful, more dynamic, and more complex. The era of the giant Jurassic browsers was fading. The Cretaceous was a world of specialized niches, bizarre adaptations, and a dizzying array of feathered predators. But the ultimate expressions of this Cretaceous dynamism were still tens of millions of years in the future, waiting in the heart of the broken continents. Chapter 19. The Narrow Continent, 75 million years ago. As we enter the late Cretaceous, the world map is beginning to look familiar, yet profoundly alien. South America, Africa, India, and Australia are now isolated islands drifting across the warm, equatorial oceans. But the most dramatic changes were happening in the northern hemisphere. North America was split in two by the western interior seaway. The eastern half, called Appalachia, was a swampy, humid landmass separated from the west by hundreds of miles of shallow, warm ocean. The western half, a long, narrow strip of land running from Alaska down to Mexico, is known to paleontologists as Laramidia. Laramidia was a biological pressure cooker. It was a long, thin corridor of land, bordered on the west by rising volcanic mountains, the ancestors of the Rockies, and on the east by the sea. Because the land area was restricted, animal populations could not spread out to find new territory. They were forced into intense competition with one another in a confined space. This intense competition bred extremes. The flora of Laramidia had completely transformed. The conifers were still there, but they were now joined, and in many places overshadowed, by a dense understory of flowering shrubs, early broadleaf trees, and strange, ancient relatives of magnolias. The ground was still grass-free, but it was covered in a thick, tangled mat of ferns and early angiosperm weeds. It was on this narrow, lush corridor that the most iconic ecosystem in Earth's history evolved. To process this new, tough, fast-growing vegetation, the ornithopods of Laramidia reached their evolutionary zenith, the hadrosaurs, or duck-billed dinosaurs. If Iguanodon was the prototype for chewing, the hadrosaurs were the Formula One race cars of mastication. They were incredibly successful, making up the vast majority of large herbivore biomass in the late Cretaceous. Animals like Edmontosaurus and Maiasaura grew to lengths of 40 feet and weighed up to 4 tons. They traveled in herds that numbered in the thousands, migrating along the coastal plains of Laramidia. Their most extraordinary feature was hidden inside their mouths. A modern horse has a set of high-crowned teeth that wear down over time. A hadrosaur had something entirely different, a dental battery. If you were to look inside the mouth of an Edmontosaurus, you would not see individual distinct teeth. You would see a single, continuous, flat, grinding surface, much like the surface of a millstone. This surface was made up of hundreds of individual teeth, stacked in vertical columns. As the top tooth wore down from grinding tough plant matter, the tooth beneath it would push up to replace it, and the one beneath that. A single hadrosaur could have over 1,000 teeth in its mouth at various stages of eruption. It was a self-sharpening, endlessly regenerating, biological grinding machine. They could eat practically anything: tough cycads, fibrous conifer branches, and the abrasive, silica-rich leaves of the new flowering plants that would wear down the teeth of any other animal in weeks. But the hadrosaurs are most famous for their crests. While Edmontosaurus was flat-headed, others like Parasaurolophus and Corythosaurus sported bizarre, elongated, tubular crests projecting from the backs of their skulls. For decades, scientists thought these crests were snorkels, used when the animals swam. Early paleontologists mistakenly believed hadrosaurs were fully aquatic. We now know this is false. The crests had no opening to the throat. Instead, they were complex, resonating chambers. By blowing air through their nasal passages, a Parasaurolophus could produce deep, low-frequency, booming sounds, like the notes of a giant trombone. In a dense, foggy Cretaceous forest, or across the vast floodplains, these low-frequency sounds could travel for miles. They were used for communication, to keep herds together, to warn of approaching predators, or for males to advertise their dominance and fitness to females. The larger and more complex the crest, the more imposing the sound. It was an evolutionary arms race of acoustic architecture. Sharing the Laramidian floodplains with the hadrosaurs was another dynasty of herbivores, one that achieved a level of defensive armor never before seen in the dinosaurian record. These were the ceratopsians, the horned dinosaurs. The ceratopsian lineage began modestly in Asia, with small bipedal animals like Psittacosaurus, a beaked creature barely 3 feet long that looked somewhat like a parrot-lizard hybrid. But when they crossed the land bridge into North America, they exploded in size and defensive capabilities. By the late Cretaceous, they had evolved into the Ceratopsidae, massive, four-legged rhinoceros-like tanks. The most famous of these is, without question, Triceratops. Triceratops horridus was a behemoth. Weighing between 8 and 12 tons, it was as heavy as a modern African elephant, but built much lower to the ground. Its body was a massive barrel-shaped cylinder of muscle and bone. Its tail was short and powerful. But the head of Triceratops was its defining feature. It was enormous, taking up nearly a third of the animal's total body length. It bore a massive, bony neck frill, a shield of bone extending backward from the skull, covering the neck and shoulders. And jutting forward from the skull were 3 massive horns, 2 3-foot-long horns above the eyes, and a shorter, thick horn on the nose. For a long time, the frill was interpreted purely as a shield against predators, and indeed, it provided some physical protection. But modern analysis reveals a more complex story. The bone of the frill was highly vascular, riddled with channels for blood vessels. In a living Triceratops, the frill would have been covered in a layer of skin, rich with blood vessels. By flushing blood into the skin of the frill, a Triceratops could change its color, flashing red or bright patterns to signal aggression or to intimidate rivals. It was a billboard, a signaling device for intra-species communication. The horns, however, were strictly business. We have direct, undeniable fossil evidence of what those horns were used for. Paleontologists have found Triceratops brow horns with deep gouges and scrape marks on them. The spacing and shape of these gouges perfectly match the brow horns of other Triceratops. Furthermore, we have found fossilized frills with massive circular puncture wounds, the exact diameter and spacing of a Triceratops brow horn. These animals fought. They locked horns in mortal combat, twisting and shoving just like modern rams or deer. The punctured frills show that these fights were brutal and sometimes fatal, with one male driving his horn straight through the frill of his opponent. But the wounds also show healing, proving that the animals often survived these clashes. It was a violent, high-stakes game of dominance, ensuring that only the strongest, most genetically fit males passed on their genes. And when the horns were not turned against each other, they were a formidable defense against the resident apex predator of Laramidia. In the Jurassic, the role of the apex predator belonged to the allosaurs and the megalosaurs. But as the Cretaceous progressed, these large carnosaurs began to disappear. The ecological niche of giant killer was left vacant. Into this void stepped a family of theropods that had been lurking in the shadows for millions of years, the Tyrannosauroidea. The early tyrannosauroids were small, lightly built animals. Guanlong, a primitive tyrannosaur from the Jurassic of China, was only about 10 feet long and weighed a few hundred pounds. It had a narrow, crested skull and long, 3-fingered arms. Another early form, Dilong, which translates to emperor dragon, was a tiny, feathered predator the size of a large dog. But as the giant allosaurs died out in Asia and North America, the tyrannosauroids underwent an evolutionary phenomenon called gigantism. Over a span of roughly 15 million years, a mere blink of an eye in geological time, they inflated in size. Their skulls widened and deepened. Their teeth became massive, thick, and serrated, shifting from slicing blades to bone-crushing spikes. Their necks became heavily muscled, and, bizarrely, their arms shrank. From the long, grasping arms of Guanlong, they evolved into the comically small 2-fingered appendages of Tyrannosaurus rex. Why did their arms shrink? Because they no longer needed them. A massive allosaur like Saurophaganax used its arms and claws to grapple with prey. T-Rex abandoned grappling entirely. It relied entirely on its mouth. Its neck and jaw muscles became so powerful that its arms became evolutionary dead weight, shrinking to reduce the animal's metabolic cost. Tyrannosaurus rex arrived on the scene in the very last 2 million years of the Cretaceous. It is the ultimate expression of the giant theropod. Standing 12 feet high at the hip, stretching 40 feet from nose to tail, and weighing between 9 and 12 tons, It was the largest terrestrial predator to ever live in North America. It was an ecological sledgehammer. Its senses were hyper-tuned. Casts of the T-Rex brain case show that its olfactory bulbs, the part of the brain dedicated to smell, were absolutely gigantic, taking up a disproportionate amount of the skull. It could smell a decaying carcass, or a terrified hadrosaur hiding in a forest from miles away. Furthermore, T-Rex had forward-facing eyes, unlike many predators that have eyes on the sides of their heads, giving them a wide field of view but poor depth perception. T-Rex had binocular vision. Its fields of vision overlapped significantly. A T-Rex had better depth perception than a modern hawk. It could judge distances with millimeter precision. And then there was the bite. Computer models based on the immense cross-sectional area of T-Rex jaw muscles estimate its bite force at nearly 12,800 pounds per square inch at the back teeth. It could bite down with enough force to shatter the femur of a triceratops. It didn't just eat flesh, it crushed bone. We know this because paleontologists have found T-Rex coprolites, fossilized dung, packed with thousands of tiny, partially digested bone fragments. For decades, a fierce debate raged in paleontological circles. Was T-Rex a predator or a scavenger? The answer, definitively, is both. It was an apex opportunist. If a triceratops died of disease or old age, T-Rex would happily gorge on the carcass, using its massive bite to crack open the bones to get at the nutrient-rich marrow inside. But if a living Edmontosaurus wandered too close, T-Rex was entirely capable of an explosive ambush, using its massive thighs to accelerate to surprising speeds and delivering a single, fatal, bone-shattering bite to the prey's spine or neck. Imagine standing in the Hell Creek Formation of modern-day Montana exactly 66,000,001 years ago. It is the very end of the Cretaceous. The air is thick, humid, and smells richly of decaying vegetation, damp earth, and the musky scent of giant reptiles. The western interior seaway has just begun to retreat, exposing vast, flat coastal plains cut by winding, muddy rivers. A forest of towering, bald cypresses, ancient relatives of oak and walnut, and thick undergrowth surrounds you. The ground is soft, muddy, and tracked with footprints. You hear a low, resonant, booming sound echoing through the trees. A herd of Edmontosaurus is moving through the brush, grazing on the low-lying shrubs. They move in tight family groups, females guarding their nests in the muddy banks. Suddenly, the ground shakes. From out of the tree line, a massive triceratops emerges. It lowers its head, its three horns catching the dappled sunlight filtering through the canopy. It snorts, blowing dust from its nostrils, and plods forward to drink from the river. In the distance, a flock of small feathered theropods, Avosaurus and early true birds, flit through the branches, chirping. Small furry mammals, the distant ancestors of us, scurry in the underbrush, foraging for insects, keeping a wary eye on the sky where huge pterosaurs like Quetzalcoatlus with wingspans of 35 feet soar on thermal updrafts like giant skeletal vultures. Deep in the shadows of the cypress forest, two bright amber-colored eyes are watching. A massive dark shape shifts its weight. A T-Rex stands perfectly still, its binocular vision locked onto the flank of a straggling Edmontosaurus. Its feathers, thin, bristly proto-feathers along its neck and back, ripple slightly in the breeze. It is the pinnacle of 165 million years of dinosaurian evolution. It is a perfectly balanced, incredibly complex, functioning ecosystem. It is the peak of the Mesozoic era. It looks permanent. It looks invincible. It looks like it will last forever. but in the cold, silent void of space, 62 miles above the Earth's surface, a rock is falling. For 165 million years, the dinosaurs ruled a world that seemed perfectly tailored to their existence. The climate was stable, the flora was abundant, and the continents provided endless evolutionary islands for them to conquer. They had survived volcanic apocalypses, shifting continents, and swinging climates. They were the most successful terrestrial vertebrates in the history of the planet. They were completely unprepared for what was coming from above. In the cold, silent vacuum of space, 50 million miles away from the sun, a rock was falling. It was an asteroid, a remnant from the chaotic early days of the solar system that had never coalesced into a planet. It was roughly 6 to 7 miles in diameter, smaller than some of the largest sauropods, but infinitely more devastating. It was shaped like a slightly flattened potato, composed of dense rock and heavy metals, tumbling silently through the void at a speed of roughly 12 miles per second. It had been on this collision course for millions of years, its path utterly indifferent to the vibrant, bustling biosphere of Earth. 12 hours before impact, the asteroid entered the Earth's upper atmosphere. To the dinosaurs below, it was still invisible, hidden by the curvature of the planet. But high above, the thin veil of gas began to react. The rock compressed the air in front of it so violently that the atmospheric gases turned into superheated plasma. For a few brief hours, the asteroid was the brightest object in the sky, outshining the sun, a blinding, furious pinpoint of light moving across the cosmos. The last dawn of the Mesozoic era broke over the western interior of North America. The Triceratops drank from the river. The T-Rex shifted in the shadows. The hadrosaurs chewed their cud. None of them looked up. None of them could have comprehended the danger even if they had. At precisely 10 a.m. local time, the end began. The asteroid struck the shallow, warm waters of what is now the Yucatan Peninsula in Mexico. The ocean was only about 300 feet deep at that point. To a 6-mile-wide rock traveling at 12 miles a second, the ocean was not a barrier. It was barely a puddle. The asteroid hit the seabed in less than a second. The laws of physics took over with merciless efficiency. The kinetic energy of the impact was equivalent to roughly 100 million megatons of TNT. To put that into perspective, the bomb that destroyed Hiroshima was 15 kilotons. The Chicxulub impact released the energy of 10 billion Hiroshima bombs, detonated simultaneously in the exact same spot. In the fraction of a millisecond it took for the asteroid to vaporize, the Earth's crust liquefied. The rock punched a hole into the lithosphere 20 miles deep and over 100 miles wide. A void was created beneath the Earth. The surrounding rock rebounded, collapsing inward and then shooting upward, creating a transient peak that was briefly higher than Mount Everest, before collapsing back into a ring of rugged mountains. The seabed was composed largely of gypsum and anhydrite, rocks rich in sulfur. The heat of the impact vaporized these rocks instantly, injecting billions of tons of sulfur dioxide, water vapor, and carbon dioxide into the stratosphere. Then came the ejecta. Solid rock, melted glass, and superheated plasma were blasted upward out of the crater at escape velocity. Some of this material was launched so high it left Earth's atmosphere entirely, orbiting the planet briefly before falling back. The rest formed a massive, expanding plume that rose into space and then bloomed outward like a mushroom cloud the size of a continent. 1,000 miles away from Ground Zero, in what is now the Hell Creek Formation of Montana, the world ended not with a bang, but with a blinding flash of light. It took the thermal pulse approximately 10 to 15 minutes to reach the northern plains. The sky, which had been a normal Cretaceous blue, suddenly turned pure, blinding white. The intense thermal radiation from the expanding ejecta plume heated the upper atmosphere to thousands of degrees. Within moments, the ground surface temperature in Montana spiked to over 400 degrees Fahrenheit, 200 degrees Celsius. It happened so fast that the large animals had no time to react. The Triceratops standing in the open forest, the Edmontosaurus wading in the river, the T-Rex stepping out of the shadows, their skin instantly blistered and charred. It was not a fire, it was a flash roast. High in the atmosphere, the vaporized rock cooled and condensed into billions of tiny glass-like spheres, spherules. As these glass beads rained back down to Earth, they friction-heated in the atmosphere, becoming red-hot once again. A rain of searing glass fell across the North American continent, slashing through the air at supersonic speeds and igniting everything flammable on the ground. The forests exploded into firestorms. The vast conifer and fern forests of the Cretaceous became a global inferno. Thick, black, toxic plumes of smoke shot up into the stratosphere, mingling with the impact ejecta. In the sky, the giant pterosaurs, including the massive Quetzalcoatlus with its 35-foot wingspan, were literally roasted in midair, tumbling from the heavens like stones. Those creatures hiding in underground burrows or deep underwater temporarily survived this first wave of slaughter, but the surface world had been comprehensively sterilized. The thermal pulse ended within hours. The global firestorms eventually burned themselves out over weeks or months, as there was not enough unburned vegetation left to sustain them. But the true catastrophe was only just beginning. The impact had injected billions of tons of sulfate aerosols, soot, and ash into the stratosphere. These particles formed an opaque shield that completely blocked out the sun. The Earth was plunged into darkness. Not the brief darkness of an eclipse, but a profound, absolute night that lasted for months, perhaps even years. Global temperatures plummeted. A world that had been tropical and temperate was thrown into a brutal, impact winter. Global average temperatures dropped by tens of degrees. For plants, this was a death sentence. Photosynthesis stopped. Without sunlight, the phytoplankton in the oceans died, collapsing the base of the marine food web. On land, the flowering plants, conifers, and ferns withered and died. The collapse of the food web was bottom-up. The giant sauropods had already vanished from North America millions of years prior, but the herbivorous dinosaurs, the hadrosaurs and ceratopsians, faced a slow, agonizing starvation. With no leaves to eat, their massive bodies could not maintain their heat. They fell in droves, their bones littering the dark, frozen swamps. And as the herbivores fell, the apex predators followed. The T-Rex, the pinnacle of evolution, starved within weeks as there was no carrion left to scavenge. Its bone-crushing jaws were utterly useless. Acid rain was another killer. Nitrogen and oxygen in the atmosphere had combined under the extreme heat to form nitrogen oxides, which reacted with water vapor to form nitric acid. Combined with the massive amounts of sulfur dioxide from the vaporized seabed forming sulfuric acid, a toxic rain fell upon the earth. Lakes and rivers acidified, killing freshwater fish and amphibians. The soil was poisoned, preventing plants from sprouting when the darkness finally lifted. It was not an instant end. The extinction of the dinosaurs was a slow, painful process spanning months or years, characterized by starvation, freezing, and despair. When the dust and sulfates in the stratosphere finally settled, allowing the sun to shine on the earth once more, the world was unrecognizable. The great forests were gone, replaced by a bizarre, monotonous landscape dominated by ferns. Ferns are disaster species, reproducing via spores that can survive in the soil for long periods without sunlight, allowing them to quickly colonize devastated ground. The large animals were gone. No land vertebrate weighing more than 25 kilograms had survived. The pterosaurs had vanished from the skies. The marine reptiles, the mosasaurs and plesiosaurs, were gone. The ammonites, those beautiful, spiraled cephalopods that had navigated the oceans for 300 million years, were extinct forever. If you stood on that fern-covered wasteland, the most striking feature was the sound, or rather, the lack of it. There was no low, resonant booming of hadrosaurs echoing through the valleys. There was no dull thud of ceratopsian horns clashing. There was no roar of a massive apex predator. There was no heavy rustle of giant wings in the air. The earth had fallen into an unprecedented, heavy silence. 165 million years of evolutionary masterpiece had been wiped clean. Geologists know this exact boundary. All over the world, in the rock layers dating to 66 million years ago, there is a thin, distinct layer of strange clay called the KPG boundary, Cretaceous-Paleogene boundary. This layer of dirt is only an inch thick in some places, but it contains the forensic evidence of a planet's demise. Shocked quartz, tiny glass tektites, and, most crucially, an anomalously high concentration of iridium. Iridium is incredibly rare in the Earth's crust, but highly common in asteroids. That thin layer of clay is the ash of the dinosaurian empire. But the story of the dinosaurs is not solely a story of extinction. It is also a story of survival. If you stood on that sunlit fern wasteland and looked very closely into the underbrush, you might see a tiny movement, a small creature scurrying through the dead leaves. It was tiny, perhaps the size of a modern pigeon. It was covered in feathers, which had initially evolved to insulate it against the cold of the impact winter. It had a long, bony tail and small teeth in its beak. It was a descendant of Archaeopteryx, or a closely related Maniraptoran theropod. It was a dinosaur. More specifically, it was an avian dinosaur. For a long time it was believed that birds were a separate group that had evolved before the dinosaurs went extinct. Modern phylogenetics, the science of tracing evolutionary relationships through DNA and bone structure, has delivered a shocking, irrefutable conclusion. Birds are not merely the cousins of dinosaurs. Birds are dinosaurs. They are the only surviving branch of the theropod dinosaurs. Today, when you hear the chirp of a sparrow outside your window, when you see a pigeon strutting on a city square, or an eagle soaring overhead, you are not looking at modern birds. You are looking at surviving, feathered theropods. Biologically and taxonomically, a sparrow is more closely related to a T-Rex than a T-Rex was to a Triceratops. The dinosaurs didn't completely die out. They merely shrank in size, grew feathers, took to the trees, and conquered the modern skies. How did these specific survivors endure the apocalypse? Because they possessed the exact traits the giant dinosaurs lacked. They were small, requiring very little food. They were omnivorous or seed-eaters. The impact winter triggered a proliferation of seed-bearing plants that were dormant in the soil, providing a food source when all green foliage was dead. They could fly or hide in burrows, escaping the lethal thermal pulse. They grew rapidly and bred in high numbers. In the ruins left by the dinosaurs, another group stood up: the mammals. The heroic narrative that mammals replaced the dinosaurs because they were somehow superior is scientifically inaccurate. Mammals coexisted with dinosaurs for over 160 million years. During the Cretaceous, mammals were forced into marginal niches, usually the size of mice or shrews, largely nocturnal, to avoid being eaten by dinosaurs. They did not outsmart or outcompete the dinosaurs. They simply got lucky. They were exactly small enough, exactly hidden underground, and exactly low enough on the metabolic scale to survive the nuclear winter. But with the dinosaurs gone, the ecological niches were infinitely vacant. Over the next 65 million years, the Cenozoic era, mammals underwent the exact same adaptive radiation the dinosaurs had experienced in the Jurassic. They grew large, filling the herbivore niches, evolving horses, elephants, rhinos, and the apex predator niches, evolving saber-toothed cats, wolves, and, eventually, us. We, Homo sapiens, are the descendants of those surviving mammals. We live in a world shaped by an asteroid impact. If that rock had arrived just 4 minutes later on that fateful day, it would have hit the deep ocean rather than the shallow, sulfur-rich seabed. The vaporized sulfate rock would not have been launched into the stratosphere. The impact winter would have been milder, and the dinosaurs might well have survived to rule the Earth for another 100 million years. Mammals would still be trapped in their nocturnal, micro-ecological niches. There would be no primates, no apes, no humans. Earth's history is written in the ink of pure chance. Look back at that 165 million years of rain. The documentary history of the dinosaurs is not merely a tale of monsters and bones. It is a foundational lesson in how a planet operates. It tells us that life is tenacious, capable of recovering from the most absolute devastation. But it is also fragile, entirely subject to the blind roulette wheel of cosmic mechanics. The bones of the dinosaurs sleep in the rock, turned to stone. The only evidence of their existence is the mineralized calcium phosphate we dig out of the earth. But their legacy is everywhere. They shaped the evolution of mammals. They provided the blueprint for the most diverse class of modern animals, the birds. And their existence altered the very soils and plants of the Earth's surface. Empires fall, oceans dry up, mountains rise and are weathered into dust. On the scale of deep time, nothing is permanent. But the dance of life goes on, shifting from one form to another, forever adapting, forever struggling, forever moving forward. That is the documentary history of the dinosaurs. A story of rising from the ashes, conquering a world, and ultimately returning to the ashes. And it begins and ends with that incredibly fragile, pale blue dot floating in the dark.